And first, I would like to look at the context of today's program. First, briefly go through the program that you see here. So, as you can see, we intend to end at after about 2 hours with a little break included. And just to point out, I know that there's different people joining different meetings. So I'd like to point you to the program of the various hands-on workshops that are being organized for ERNs. So this is workshop 6, if I count correctly, and your next opportunity is already tomorrow when there's a Pheno Packets hands-on workshop. You can find information on the EJP teams or on the teams side, and more are coming up early May, and we have program up to June. So if you think any of those are interested, don't hesitate to sign up and join for those. And with that, I'd like to hand over to Carl to briefly introduce the EJP RD virtual platform, which provides the context for the topic that we discussed today.
Yes, thank you, Ronald. And then I took over control. Yes. I hope that worked, but we will see in a minute. So, yes, it works. Just to give you a little bit of context, the EJP virtual platform is an effort located in work package 12 of the project. And I would like to take the opportunity in the next 5 minutes to give you a brief overview of what this virtual platform is and what it can do. So I've tried to come up with a sort of definition. What is this virtual platform? It's an interlinked echo system of resources and services. And why do we want to have that? It's all about fostering and facilitating research in the rare disease domain. So why is it an ecosystem? For starters, it's all about software and services that are provided by the virtual platform to achieve that goal. But it's not only services and tools, it's also about guidelines, how to do and build things, and of course data format. And the sum of that all make the virtual platform into an ecosystem. It's also important to know or to define what the virtual platform is not. So do not expect a centralized all-in-one platform where we are feeding in everything, all the data and all the tools that are there. That's not what the virtual platform is. It is by design a federated and distributed thing. So I would like to come back to the interlinked aspect of the virtual platform. So looking at the rare disease domain, it's all about resources and things that are already in place, that are out there. It's about registries and catalogs and tools. And so the goal of the virtual platform is, somebody's posting that we cannot see slides. Is that right?
Yeah, I see them. I don't know if there's others. I know it is a...
Yeah, we see them.
Common glitch.
I can see them as well.
Okay, thank you. So it is a common glitch in Teams, and then it may be good to leave and rejoin. Usually that solves the problem, hopefully.
Okay, thank you. So coming back to the idea, so it's all about registries and catalogs and tools and services we have out there. And the whole idea is that we create links between all these registries and catalogs, and that we make data accessible and findable. So it's all about, to put it in another way, it's all about connecting the dots in the rare disease domain. And that's where the virtual platform as an ecosystem jumps in. So it's all about helping to create this linkage, this interlinking of services in 4 ways. For starters, it's by providing services in the area of authentication, consent management, record linkage, metadata services, and verification. and of course data discovery and querying. So it's not a taxative list. It's what is envisioned right now, but something that will certainly grow. And it's also important to emphasize that it's not an activity of building things from ground up, because there are already a great variety of tools and services out there, and it's pretty much about bringing all what's out there into the virtual platform and provide them as services. But as I said earlier, it's not only about software and services, it's also about guidelines and how to build and create things with respect to sustainability, maintainability, quality, and GDPR. And last but not least, and that's the focus of today, it's about data formats and finding a common language to connecting the dots, and you will hear a lot about that today. So how is the virtual platform built? It's an iterative process within the EJP RD project. We have work foresight, so we have working groups that elaborate on the different aspects that I have just mentioned. And the outcome of these goes into a virtual platform specification, which again is the foundation for the development of new tools and services. And then, after all, this process starts again with refinements and new things to be added. Why I'm sharing this development cycle with you, it needs to be stated that we are not looking at a big bang sort of deployment and all of a sudden the virtual platform magically appears. It's about going through iterations and growing things. That's what I would like to emphasize here. So to sum up, what is the virtual platform? It's an interlinked ecosystem of resources and services. It's not a one-stop shop. It's not a single place where you can go to. By design, it's decentralized and federated. It's iteratively developed, and it's all about connecting the dots of existing tools, services through helping services, through guidelines on how to create things, and especially about finding a common language to connect the dots by providing common data formats. And having data formats, I would like to give back to you, Ronald. Thank you.
Thank you. I think that's very helpful to get some context and indeed be very clear that it's not about a centralized repository, but indeed connecting the dots. And that's a thing where a challenge comes in because, of course, with this connection, we intend to some extent cater for the variety of things that exist out there. But on the other hand, you can imagine that, we need to set some constraints and some requirements on what we can deal with in such a linked ecosystem. And to really drill it down to the basics, I thought it's good to briefly reflect on data formats in general before we dive into some examples given by the EDC vendors who provide their data in a variety of formats. I think there's people who think that formats really, don't matter and that it's basically you can do whatever you like. And to some extent that may be suggested by the possibilities provided by various software. So as an example, I took text processing, MS Word, Adobe Acrobat, and Notepad. And we see that there's a whole bunch of formats that they have in that they can export to. We see that Word can even go to PDF, and PDF can save as Word. So it seems like it's all the same. And of course, there is a lot in common, but there are also differences, and I think that's most clearly shown in the Notepad example that basically does text. And that means that everything that you would have in a Word document or in a PDF, if you would save it as plain text, there's a whole lot you lose. There's formatting, bold, italics, things like that are not available anymore in your text document. And well, I think you will hear more in this session also about metadata. In, for example, Word or PDF documents, there is metadata about the author of a document, sometimes things like the editing time of a document. So that's all information about the document, which is, well, kind of hidden from the text in the document, but is added as metadata. And like I say, that is available in things like Word and PDF, but not available in a text document. So similarly, what we will look into, if you look into your data formats for your rare disease data, it's important to think what would be a proper format to use. And I just took basic examples, and we'll dive a little bit deeper step by step through this session. So here as an example, you see that it's basically not only the format that you provide, so whether you would show a, well, like I said, the text or the Word document, but it's also the model in which you present the information. So here I took a simple comma-separated values, or maybe even Excel example, where you could present the same information in different ways. So here's information about 3 people, and here's information about 3 people. But here, diagnoses on the top we have a diagnosis 1 with date 1, diagnosis 2 with date 2, and so on. Whereas in the model below, the diagnoses have been separated from the patients, and patients are referenced by IDs. And to make it even more complex, and that's also one of the things, of course, we need to take into account, IDs of patients throughout resources may be the same, but may not refer to the same patients. So if you would take a look here, you will see that patient 1 in the top example is not the same as patient 1 in the bottom example. That's actually patient 3, if I'm not mistaken. So that's the kind of things that we need to agree on, what formats to choose, what models to choose, how to adequately identify individuals and diseases. And why we're doing that is, well, basically 3 things that we like to do. So first, we like to be able to search for data sets, because it's, well, I took the needle in a haystack example. If you want to search a needle in a haystack first, you need to have a haystack. So for rare disease data, especially, the question can be, is there anyone who has information about a certain type of patients? So you would look for data sets. In other words, you would look for haystacks. And then if you know what haystacks could potentially contain the data that you're interested in, the, well, say, needle, you could look into the haystack and actually find out there's not a needle in it, but a buffalo. So processing the data sets is then the second step. So finding is 1, searching in them is 2. And once you've found the data, you can analyze. And for example, you can look into family relationships of resources that you have retrieved. So that's the kind of information that we'd like to enable to be enabled, that has been made available through the open, the virtual platform. And well, like I said, that depends on the way in which data is presented. and for some examples on how data can be represented and how that's done in current systems, electronic data capture systems, I'd like to hand over to Martijn and Yuri, who will give some examples from the systems that they work with.
Great. Shall I take control of your screen?
Yes, go ahead, Martijn.
Let's hope it works. Yes. Yes, so I was asked to give you a short presentation of how the export formats of the Castor EDC platform works, and various registries also work with Castor, an electronic data capture platform, where you can collect data from patients on forms that you've built in the system, but also export the data, of course, to analyze it. So I would just give you a quick overview of all the formats that we support. So if you click the export button in our software system, you get a pop-up that asks you in what format you want to export your data. But that pop-up asks you if you want to export your data in a CSV format or Excel or as SPSS, since some researchers also use SPSS to do their data analysis, and that data format is slightly different from CSV or Excel. And we support also subsets of data that you can export. So on the left you can see the pop-up that we show, or the options that we show to the users if they want to export their data. So you can choose if you want to export your options as numbers, so the coded values that Roland also showed in his example in the Excel format, but also, for example, as labels. So instead of using 1 or 0 for female or male, you can also use the labels if that's a bit more readable for if you want to get an overview of the data. And then you can use, for example, a tree to browse through your study. I'm not sure if you can see my pointer, but you can use a tree for that, or you can just paste the specific variables that you want to export. So that's one option. So exporting your data in a tabular-like structure as CSV or Excel or SPSS. But we also have an API where you can either import or export data from the system using other software systems. So you can integrate with our platform, and about 70% from all the traffic that we get in our system is from our API. So we see that a lot of users actually integrate with the platform rather than take the data out manually. So that's a possibility, so that it actually is integrated in the workflow of your registry. And moreover, we also have an R package, so you can export your data as SPSS, as I've shown before, but also as with an R library that allows you to import your data in R in real time, so you don't have to go through the user interface, but run your R script to do your analysis and get the data from the system there. And lastly, we also support RDF, which also will be covered throughout the rest of this presentation. But that's a format that allows you to express the relationships that are available in your registry, in the data of your registry. So you map your data that you have in our EDC system into a common data model, so the data model from the ERNs. And then you can either query or export the data in that structure and combine it with other data from other registries. So that was a quick overview of the formats that we support at Castor.
Okay. If it's okay, then I think I should take control from you. Yes.
Yep, go ahead.
Thank you.
And just to point out, I don't think the pointer is actually showing. So if you're indicating something, it didn't. I don't think others see it. At least I didn't.
No, me neither.
No, I'm sorry about that.
No, that's no problem. But just so that other presenters know, pointers aren't shown. Yeah.
So I'd like to give a similar overview, except formal genus, which is also being used by quite a number of ERNs. So I have a couple of sections. The first one is import formats. I thought it might also be interesting to cover that. So the first one is the most obvious. It's your hands. It's where you just open basically a data capture form, and you type in the things that go into the database, and you click Save. I suppose the second least technical is the Excel. So you can just put all of your table structures and the data that belongs to the tables in a relatively simple Excel format, and just drag or browse and click Upload, and that's also a way to put it in the database. The third one is if you're for some reason you'd like to use CSV files, which is more easily exported from programming languages and stuff like that. You can also bundle those and upload them in a zip. And if you're even more technical, you can choose to go for JSON, which is number 4, or YAML, which is number 5, which you can include the table structures and the data. So there are multiple ways, and underneath this are actually APIs that accept these types of files and these types of posts and get commands. And so there's also other ways, for example, via R or curl, to interact with the imports. Well, then, if you've imported, obviously you can browse, filter, and query your data in a browser type screen like this. You can delete individual rows or edit them, or well, anything you expect from an EDC like this. And then once you're done, you want to share your data or your results, you can go to the export options. But first, I want to mention one thing, because it'll come back in the last slide that I have, is that the structure of your data itself is editable. So you're not stuck to a particular model, a particular way of expressing your data. If you want, you can still say, I need an extra column, or I want to change the data type of a column, or even the semantics of a column. So you can, in this case, a super user has the power to change the definitions of your data while it is in the database. So this allows you a bit more flexibility in terms of adjusting your needs on the fly. And once you're happy with all of this, of course, then you can start to share. So that's my last slide. So there are also quite a number of export format options, in a sense surprisingly similar to Castro, I believe. So first, so you can actually export several flavors. So you can also just export the schema, which is just the definitions of your tables. So that then you don't export the actual data, but the model. So you can share, if you have a particular structure that you're using, you can just share that structure without exporting your data. Of course, you can also just export the data in your database, and that can happen via several formats. So I already mentioned Excel and CSV, but there's also a basic RDF export based on the column semantics and JSON LD. And of course, you can also choose to export specific tables. And I think if you select columns, you can also download via the browser. You can download specific pieces of your data. So all of that should not come as a surprise, but yeah, so there are quite some ways to import and edit, manage, and then export your data. And this is also compatible with APIs, as I mentioned, that you can use command line or via R or programming language. You can just talk to the REST API, for example. So that's it for me.
Okay, thanks. So I think it's interesting to hear that you're basically adding one more thing to the data formats and models, and that's the fact that I think we're all quite used to well, exchanging files, but that, well, one part of this larger ecosystem is APIs. So basically opening up data not by sending it directly as a file from A to B, but making it available through some service with which can be communicated. And I think we'll later on in this session also we'll see the role that those APIs play. And I think from that perspective, you'll also understand that, well, like I said, you can't simply cater for unrestricted choice of formats and models. Similarly, you can't cater for an unlimited number of APIs through which data are provided. So, well, within the virtual platform developments, we are trying to be, well, not so strict that we say there is just one model to rule them all, to which everyone has to conform. But like I said, if we would say, well, everyone just does whatever he or she likes within an ERN, then making the conversion and making this virtual platform would simply not be possible. So the combination of data formats and models on one hand, and APIs on the other hand, play an important role in establishing this virtual platform. And with that, I would like to dig a bit deeper into the data formats that are relevant for data. We saw a few already, and if time permits, I also like to do a brief example of what it means also in relation to the schemas that was mentioned earlier. So, well, the important thing, like I hope I already illustrated with the various well, word processing documents, Word, Adobe, Notepad, is that different formats have different capabilities. And I've listed a few aspects that I'd like to dig into for the data formats: CSV, so comma separated values, XML, JSON, JSON LD, and as maybe kind of an outlier, R. Martijn mentioned SPSS as an exchange data format from Castor. So that's one option. I think various statistics tools like R also provide their own export or storage formats. And well, there's different capacities being supported, and I'd like to have a look at a few of them, starting with schema and then looking at the other aspects. So, well, we discussed metadata a little bit, and well, I pointed out in Word documents you can have an author and the amount of time that was spent on editing a document. That's one type of metadata. In data documents, it's important to agree on, well, the type of data that you capture. So as Martijn and Yuri showed, you have the possibility of exchanging the model, so the schema that you adhere to. And well, that's important, and that's one of the things that's made possible, for example, in XML, where you can validate documents against a schema. And well, I'm looking at time. Yeah, I have some time to do this, so I will switch from this presentation to the browser. XML that you can validate, and well, we'll read through it, and then so I'll just copy both and then do some editing. This is really the low level validation. So what we see here is data about, well, a person, Joe Tester, who lives in Baker Street, and here is the schema that such data should adhere to. And here we see that there's an address, and well, then an address, there should be minimally one, and there can be as many as you like. And addresses consist of a name and a street, and both are optional because the min occurs is 0 and maximally it's 1. So this describes what an address should look like. And then the important thing of a validator is that it helps you to check if your data adheres to your schema. And I think normally, hopefully that's taken care of, but that may not always be the case. So what I do here is now simply putting in the data. So this is the XML document that I would like to validate. And this is, of course, you will normally not do this in such an online system, but there's all kinds of toolings and parsers that can do it for you. And then I say, okay, I want to validate it to another schema that I will add. And the schema is what we just saw. So I've pasted that here. Let me see, starts with the schema, ends with the schema. Of course, if your schema is incorrect, then everything fails. So let's see if this works. If I now validate, it says, oh, errors have been found. And actually, it was what I expected and hoped for, so it works. Because it says, okay, there is invalid content found, the wrong extra field. Well, the name gives it away already. That shouldn't be there. And it says that address must be terminated by a /address. So apparently, my text document or my XML document did not adhere to the schema. And then I can try to fix that by, in this case, well, repairing. So this is, the field should not be there, it said. So I removed that. And then it said, okay, address, closing tag. So let's see if it works now. Yeah, so here you see how schemas help to check if the data that you provide is correct. No errors were found. So having schemas and using schemas for validating your data is very important. And with that, I'll switch back to the PowerPoint. Yeah, so schemas help basically to assess the quality of the data that you provide. And we saw that, for example, CSV doesn't provide schemas, but things like XML, JSON, and JSON LD do. There's other things, nesting and arrays, which is important if you want to represent repeating data. And in my previous example, I showed how a person can have multiple diagnoses, and you could do diagnosis 1 with a date, diagnosis 2 with a date. That's things that is not easily catered for in CSV, but that is supported in, and here I take a JSON example, where you can do nesting and can do arrays. And just to elaborate a bit on that, nesting is when you basically want to represent objects, and arrays are used to represent well, multi-valued attributes. So if we see here, it's a representation of John, who is 30 years old and has 8 cars for whatever reason. We see that his cars is basically broken down in an array of 3. And that is the Ford cars, the BMW cars, and the Fiat cars. And each of these elements in this array is a nested object. And this object then again consists of a bunch of attribute value pairs. So there's name Ford and models with value, and then again an array, Fiesta, Focus, Mustang, and similarly an object with attribute name BMW and these 3 models, and then an object with name Panda and 2 Fiat and 2 models. So JSON and similarly, well, XML does provide nesting, does not provide arrays, but JSON, JSON LD, they provide both of these. So a more elaborate way to represent this kind of data. And then an important aspect is also the human readability, because there's of course the talk about fair data, and we want data to be processable by humans and by machines. And it still means that we often look at, but well, especially while we're developing all these things, we're looking at the raw data. And then the question is always, so how readable is your raw data? So first, it should be some text format and not some binary format in which data is represented. But even if it's readable, it can be hard to understand. So if we look at a JSON LD, which is JSON for linked data example, then here we see, okay, we see an array with the square brackets, and in it is an object of type person with a job title professor, the name is Jane Doe, telephone with a number, and some URL for janedoe.com. That's an ID. That's all okay, but whether this is readable or not largely depends on what you use as identifiers. So in this case, you see, oh, these are all URIs, Uniform Resource Identifiers, which is really a way to link information together. And it's understandable because schema.org/person, well, human interpretation is not too hard there. But there's also systems, vocabularies, if you will, which use names which are not so understandable. For example, they use numbers, C17029. And well, if you wouldn't have schema.org/person, but C17029, you wouldn't exactly know that this refers to a person. And that makes clear that you really would need machine support to understand what the data is about. So, well, what the best format is, well, like I say, there's no best format, but there's maybe formats which are better and which are, well, less adequate. Will depend on the way in which you want to process it and what you want to do with it. Like I said, CSV does not provide schema, so you can't validate whether the data is correct, and then correct to a certain extent, at least conformant to the schema. So CSV may, in cases, not be the best option. And also, if you want to have nested structures, it may be good to look into things like XML or JSON or JSON LD. And with that, well, the important thing is that, and maybe, or even hopefully, for many of you, this will be something that ultimately will happen under the hood, and you will not need to know everything about this. But it will be good if you know at least something about this, especially as these data will then be manipulated to be turned into a, well, homogeneous form that can be processed in the virtual platform. And for the things happening in this data manipulation, I'd like to hand over to Shushin and Rajaram. So Shushin, you can take control if you like.
Yeah, thanks, Ronald. I'm taking. Yes, so thanks, Ronald, for the introduction. It is understandable to use these data formats to deal with different situations with different capabilities. But when it comes to large-scale data integration or data exchange among multiple data sources, these formats can have some weakness. For example, they have little or no ability to automate the integration that combines closely related data from disparate sources. And even if that happens, the transformation is usually performed exclusively between two formats. Therefore, we recommend RDF, which stands for Resource Description Framework, requiring data and knowledge represented in a triple pattern: a subject, a predicate, and a verb and an object. For example, by I transform CSV, I as a subject transform as a predicate and the CSV as the object. Each component is represented in a uniform resource identifier or URI, and these URIs can refer you directly to their definitions or where they are formally defined. So this RDF structure allows to add meanings, or we call semantics, to each component, and holding these semantics, not only we humans but also machines can understand the meaning of data, which makes annotation visible. Makes automation feasible and the data integration more smooth. So the focus of transformation here is from non-RDF data to RDF data. For example, CSV, XML, and JSON are typical formats that have no RDF element, but Turtle, RDF, XML, and RDF JSON, and also JSON ALD are formats that follow RDF framework. Prior to transformation, it is necessary to know how much RDF data differ from non-RDF data. Here we take the example data of a patient called Bob, and you can see the JSON format on the left and the Turtle format on the right. Obviously and reasonably, they look different synthetically because they are different, coming from two different families. But the most significant difference is that the Turtle data uses URIs to describe the relationships between Bob and his attributes, while JSON data just used a list of strings. And if you copy these URIs to your browser, you will go to a web page that presents the definition of the term birthday from fourth ontology. And another level of difference is semantic difference, which means even if we look alike from our appearance, but either genetically or mentally speaking, we are different. Still take Bob as the example. I cannot say the name in JSON data is equivalent to the fourth name in the Turtle one, unless the person who built the JSON data declared that the name is defined as fourth name. And if we take the Turtle data as the transformed data from the JSON one, I would say this transformation is not good because there is information mismatching from sex to gender and from birth date to birthday. And here you can see another version of transformed RDF data, which looks better because the elements are converted from sex to sex and from birth date to birth date. But I'm concerned if these terms from NCIT ontology would overly interpret the sex and birth date, which might narrow the scope of components. So it is very important to define your own mapping rules as a first step in your transformation procedure, and your mapping rules should specify which data item in your own system semantically corresponds to which data element in the target model. And after that, you can implement the transformation with the help of semantic technologies in two directions. For example, from CSV, XML, and JSON to RDF datasets, RDF mapping language, and also Yarmoul can help. And Mark will give some vivid demos regarding this. And if we transform from RDF datasets to XML, then XSLT and XSparkle can help, but they are not the focus of this workshop, so I just put names here to let you know that they exist. So here is my brief introduction about transformation, and the next Rajan will introduce query, which would make good use of RDF features.
Yeah, thank you, Sushin. I will take over the control now. Okay. It's a bit strange. I can't use like the arrow key, but I can use like a mouse to move over. So okay, in my session, like I given example of like how transforming like RDF data into non-RDF data. Like I do it via like a Sparkle query. Before I show my query, let me explain like a little bit about like the technology that I'm going to use. In my case, like I'm going to use like a Sparkle, which is a query language to query like RDF documents or like graphs. And Sparkle is also like a protocol, like mostly started as a HTTP protocol to manipulate like RDF graphs, meaning like storing them, querying them, and like updating them. So on your right-hand side, you see a picture of how a triple store works. And like, when we want to like store like a data into a triple store, they mostly take like RDF files. So meaning like then you can like store only like RDF like data formats like Turtle, XML RDF, and even like some modern triple stores, they even take like a JSON LD as an input to store. Then you can like query those documents by using Sparkle queries. And when you retrieve like your result out from your Sparkle query, then you can just transform into like most of like known formats. Like for example, like most of the tabular formats like CSV and TSV, and like the XML and even JSON. So let me give like a little bit like more explanation about like Sparkle itself. So Sparkle is a user-friendly like query language. When you like a query triple store with the Sparkle query, what you basically do is like you send like a known pattern of your RDF graph to a triple store or like endpoint and retrieve like result out. And most of the triple stores, especially like modern triple stores, they do have like a REST layer on top of them, meaning like you can like query those triple stores by like REST calls, like get or like put REST calls. So I show an example of such a Sparkle query. Like here, like on your right hand side, I've shown like an example of an input file, which is again like Bob from like Sushin's example. So here, like I'm describing Bob as a patient, and some of the attributes of a Bob. In this case, like a personal attributes like sex and date of birth of a Bob. So in my Sparkle query, I want to get like all male patients. So how do you do it in Sparkle? Like on your left hand side, you see like I started like my Sparkle query with the first statement. The first word in my statement, I'm informing my Sparkle query is like I'm looking for like a list of persons. When something like starts with question mark in Sparkle, mean like you are indicating Sparkle query that you don't know what you want to have there, but you're just asking like Sparkle query to give a binding variable with a list of like values there. But I do know like what I'm looking for like in terms of like relationships and values. For example, like looking for like persons who's of type like a SIO person, and my query is not stopped there, right? Like I'm looking for like persons who's also a patient. So that's what like I'm doing in my next part of the query. So I'm saying like, okay, like you found all the persons for me. Can you also please check like if this person like played like a role as like a patient? So in this case, like I'm using like ontological terms to see like if that particular person played like a role, a patient role. So again, like my query is not finished here. So according to my query, I should find like all male patients. So then I further expand my query and indicating Sparkle like, okay, you find me like a person and who also play like a patient role. Can you also like find me like a person and whose biological sex is also like of type like male? Now I'm done with my query, at least like sending like patterns to Sparkle endpoint. Now what I have to do is like finish my query with like asking Sparkle to give me like a result back. So in this case, I'm asking like Sparkle to give me like list of persons, and I finish my Sparkle query by adding like prefixes of like predicates and objects used in my Sparkle query. And in the below, like you don't see my mouse cursor, you see like output of my query. In this case, like I'm asking like Sparkle to output it as a CSV. So yeah, in my example, I had like only one person Bob, and you see like a header, like a person as a Bob, a header, a person for value Bob. So with that, I finish my session. I will hand over to like David. We explain about like JSON and REST.
Yes, thank you. Just testing if I can forward, but I cannot move backwards. Yes, I can. Okay, thank you, Rajaram. I'm now very glad to show you an example of how query languages and data formats can be used, or how we use them to build services within the EJP platform. And as Karl Kreiner said in the beginning, this is somehow connecting different locations, so connecting these dots we saw in the beginning to build a network that can enable discovery of resources and records of patients. And when we talk about resources, we talk about the actual registries or biobanks that hold information about patients related to a certain rare disease. And when we talk about records, we talk about the actual patient samples within these registries and biobanks. So to distinguish between the two and what we have built so far within the EJP virtual platform, when we query for resources, we set this up to be a federated P2P network so that every endpoint, every peer in this network can query all the other endpoints. You'll see in a second when I go one slide further what I mean by that. So a query can be initiated at any site. So at every endpoint, every peer within this network. The data, however, is kept, the data that is being transmitted between these endpoints, however, is kept minimal, and there's only a link being shared that enables a redirect to the respective endpoints. So no data is actually being shared. There's only a link given that I can use to go to the individual endpoints. So this is enabled by a common language, or as we call it, an API, that has an underlying model that was developed within EJP, and it's using a JSON data format to enable this query handling. Yeah, so going over to the record level now, you can see the differences between resource level and record level in green. So on the resource level side, we built one whole federated network, and on the record level side, technology was implemented to enable many of these networks. And again, the query can be initiated from the EJP side or any side within this network or within one of these networks. Again, no data is being transmitted. Only links for redirection is being transmitted, and it's using not the same language as the resource level, but a very similar one designed to be for record level. And the results is again being shared as links, but in the case of the record level, it can be many different things. It can be counts, IDs, data, depending on what the individual endpoints, the individual ERNs in our case, want to share. Exactly. So this is the distinguishing between what we call resource and record level, and also what we distinguish when we talk about the services we build for the virtual platform. So going one slide further, I'm going to show you the idea of this resource level now. And this is what I explained earlier. You have this entry point of the EJP virtual platform on the right. And this entry point can query all connected resources, but also the connected endpoints can query themselves and all other endpoints that are connected to this network. Exactly. And this is enabled by this underlying model and this underlying data format. This is based on a web standard. In means of the resource level, it's based on Open API. In means of the record level, it's based on the Beacon API, which is an upcoming standard when it comes to medical data discovery. And for the resource level side, it's based on this JSON data format, which can easily be transferred into something that is SEM web compatible, so semantic web compatible, and like RDF, for example. It's using a REST design, so basically GET requests, and on the bottom you can see a sample request. You've got the catalog address, then the address of the individual service at that catalog, and followed by the parameters we use to filter our request, also to build the query. So in this case, it would be returning registries or biobanks related to the rare disease code, author code in this case, 730, and in this case, it's filtered to only show biobank examples. Okay, so I'm now trying to give you a live demonstration. Well, I forgot something first. If I send this query to an endpoint, this is how a result could look like. So it's JSON format. And it's being then the name is shared. The type is used to distinguish within the catalogs what resources are being shared. The home page is this link I can then use to be redirected to this respective resource, so to the actual network that is providing this resource. And we also share information about the publisher. So we have an institution that is responsible for the maintenance of this resource. So coming to the live demonstration, I'm trying to share my screen. I hope this works now within the. I need a confirmation that you can now see a web browser.
I see your local host.
Yes, perfect.
Yeah.
Okay, so this is the entry point to this resource discovery network from the EJP RD side. You can imagine having something like this at every endpoint that is part of this network. But we wanted also to have a neutral endpoint that can be accessed by the EJP website, for example. So this could also be built into the EJP website. And I can now simply search for an author code or a rare disease name. In this case, I'm simply choosing the Jetsi disease and I click search. And what's happening now, this query is being sent to all endpoints in the network. This can take some time as the networks within themselves need to distinguish what information they want to expose. So the information that is being sent back to me. And what we can now see is the results from the connected networks. Therefore now that is BBMI ERIC and the OrphanNet network. And I can then use these results links to be redirected, in that case, to the OrphanNet network, and everything else goes from there. So what's being shared in the end is the resource name, as you just saw on the slide before, a description about the resource, information about the publisher. In this case, I'm only showing the country this registry is hosted in, and the link that I can use to be redirected to the respective resource or the catalog that is providing this resource. Okay, I think that's it for the live demo. What I was trying to show here is an example of how models and data formats can be used to build such a service. Yeah, okay. I think it goes back to you, Ronald, right?
Yes, I will take back control. Many thanks. I think this is really great to see.
So we've been seeing a lot of different data formats. One of them that has been brought up a few times is called RDF or JSON LD, and these are different forms of what is generally called linked data. So I'm going to talk a little bit about linked data. Linked data is based on a framework called RDF, Resource Description Framework, which is a way of conceptualizing how to represent data and knowledge, and there's a variety of ways that we can implement it. But RDF basically says that all data and knowledge can be represented through a combination of very simple statements that are called triples. Much like a human language, the statements take the form of subject, predicate, and object. And if you put many of those small statements together, in principle, you can express anything. So I'm going to now introduce you to my cat. This is Stormy, and he's very sweet, and people who know me knows that he's the love of my life. So let's talk about my cat in the form of triples. So subject, predicate, object, Mark owns a cat. The cat's name is Stormy. And if we want to put those together, the object of the first triple becomes the subject of the second triple. And so Mark owns a cat. The cat's name is Stormy. Excuse me. And then we put a whole bunch more triples together. So Mark owns a cat, cat's name is Stormy, cat's breed is British Long, Mark's residence is Madrid. Madrid has a population of 6.2 million if you look at the entire surrounding area. When you put those into a pictorial format, it becomes what's called a graph. And so the graph on the right is the pictorial representation of the triples on the left. And so generally, when we talk about RDF, we draw these graphs so that people can see the entities and the relationships between them. So if we look at what these graphs consist of, they consist of three things. There are resources, which are in the blue. There are literals, which are values, actual data, which are in yellow. And then there are the predicates that connect the resources and the literals to each other. So in the context of the web, RDF has some really interesting properties. What you do is you say, well, let's say that every resource is actually a URL and every predicate is a URL. And so then your graph looks like this. In the center, we have the resource, which is pet registry MDW112 pets 112 cat. That's my cat. And its name coming from the FOAF, the friend of a friend ontology. Name is Stormy, and it has a breed, which is British Long. Now, the benefits of doing this are numerous, but I'll talk about just a couple of them right now so you get a feeling for why the EJP is using this particular technology. So first of all of those URLs are globally unique. So the URL MDW112 cat is a unique identifier for my cat. And those predicates, the FOAF name predicate and the predicate relations has breed, are also globally unique. But not only are they unique, they're shared. So everyone in the world is allowed to type into their browser or into their database MDW112 cat if they want to talk about my cat. Everyone in the world uses FOAF 0.1/name as the predicate to point to a name. And then similarly, the breed one I just made up, but in principle, there would be a predicate that everybody would be using to describe that particular relationship. So everyone can use exactly the same identifiers, meaning that everyone is allowed to talk about anything in the world in exactly the same way. And more importantly, that middle address, if you're not used to RDF, you'll think that's a website. It's not. It is the identifier of my cat, the thing that is sitting beside me right now purring. It is the ID of my cat, not the ID of my cat's website. They're not the same thing. So we have virtual twins in the virtual space for the things in the real world. But I can send my machine to that address, and it can look up what information about that thing that's in the real world. The second benefit of RDF is because of this uniqueness property. So on the left, I have my information about my cat. So I'm in the center, the cat is in the center of the graph, the name is Stormy, and the breed is British Long. And then on the right-hand side, we have the graph from the pet shop. So the pet shop where I got my cat, it has information about MDW112 cat. The predicate is has parent, and the parent is LA0 pets LA099. And that name of that cat is Snuggles. Because we are both using the same identifier, which is globally unique, to talk about my cat, it then becomes possible, so these are two, it becomes possible to merge the statements that are about the same thing, right? So the blue node on the left and the top blue node on the right are exactly the same. They're identical in both of our databases, which means that if we simply merge the databases, those two nodes become the same thing. Right? In fact, they are the same thing. So what happens if you imagine this unified graph is that I take the node on the right and I flip it down, and it becomes coincident with the node on the left about my cat. The property that joined that to LA099 flips down and now becomes LA099 has, sorry, my cat has parent LA099, and the two graphs merge. And machines can do this data integration completely automatically. So, and in fact, it is so simple to do this that you literally concatenate the data sets. You just dump one, dump the other, and then just join the two files. And that's how easy it is to do data integration with RDF, which is one of the reasons that we want to use it in the EJP. Okay, so that's the end of my little spiel about RDF. So I'll stop and hand back.
I think later on you will dive a bit deeper in that even. But before that, I would like to add one layer of complexity, if you will, and that's the fact that we need to agree on the models, or if you will, schemas, that we use within the EJP. Mark, you're not muted.
Sorry.
If you want to chip in. Or okay. So we need to agree. So because what Mark showed, like there's a name predicate, there's a breed predicate. So what we would need to do within the EJP is to see if we can agree on the predicates that are relevant to use in the rare disease area. And well, we're not alone in the rare disease area. In all of healthcare, there's a whole bunch of perspectives on harmonizing the representation of data. And basically that has introduced a number of different data models or schemas, if you will, which at a high level provide an outline for how to or what can be represented and how data can be organized and what attributes can be provided for data. And well, because there's a whole variety, we need to see how we can benefit from that, and if we would in one way or another need to restrict. And like I said earlier, if you look at the formats, we say, well, there's plenty, and we're not going to say there's only one. But similarly, we can't say, okay, we can cater with any format. And the same goes with models, where we don't want to say there's only one, but we can't cater for every model. So it's good to see what exists out there and how we can benefit from those to integrate them within the EJP virtual platform. And these, what I branded the top models, basically are sets of schemas to which data should adhere. And there's 3 coming from abroad: HL7 Fire, Omop Cdm, and CDisk, that I would like to very briefly address. And then, because there are 3, and similarly, like we're saying, well, within the virtual platform, ultimately, we want to work everything into the linked data representation. We intend to establish a linked data representation for, at least now to start with, for the common data elements in a linked data way. And that would ultimately lead to as Shushin showed earlier, to maybe lingua franca from and to which the other models can be transformed. So what exists out there is first HL7 Fire. It's a, relatively new, maybe 4 or 5 years ago established standard, largely focusing on clinical data exchange. So this is really, and that's what HL7 has been doing, and HL7 has been around for about 50 years. What HL7 aims to contribute to is the exchange of information in healthcare provision. So between laboratory systems and electronic health records, or maybe between a hospital information system in one organization and the information system in another organization. Again, when you want to exchange information, you need to agree on what to exchange and how to exchange it. So this discussion about models and formats is something that has been around for a long time, and that also HL7 intends to contribute to. So HL7 Fire in full stands for Health Level 7, Fast Healthcare Interoperability Resources. And the interesting thing, I think, is that what pops up is the resources, which is the same as in RDF, the Resource Description Framework. So it is different from RDF resources, but it has a lot of similarities. And actually, there's also work under the hood to increasingly better align them. These resources are commonly expressed as XML or JSON structures. And if we look at the most relevant resource types that have been specified within HL7, we see things like allergies, problems, procedures under clinical, and if we look under diagnostics, we see observation, specimen, imaging study, and then medication request, dispense, administration, and so on. There's much more. There's, of course, also a patient resource. So this provides one way of structuring information really from the perspective of exchanging clinical data in the process of care provision. So one way would be to say, okay, we're all going to use HL7 Fire, but like I say, it's a new kid on the block. There are other things, and each of these models has their strengths and drawbacks. So it's good to see what others exist and, how we could bring them together. The second one I mentioned was Omop Cdm, which is shorthand for the Observational Medical Outcomes Partnership Common Data Model. And the key word here is observational. So what Omop, or now called Odyssey, Observational Health Data Science and Initiative, I think, what they try to establish is to be able to perform research on data, observational data from heterogeneous sources. And to establish that, they have specified a data model, this common data model, with the idea that that's a common storage model based on which a whole set of tooling is being realized. And the idea would then be if 10 sites have their observational data represented using Omop Cdm, they can use the same set of tooling, including things like R and all tools developed within Odyssey. And they can do distributed data analysis. And this model, well, we'll see things that look similar to HL7, but we may also see things that look slightly different. So for example, well, we see person, we see things about observations, about procedures, and we see things about drug, but here's drug exposure, where there's also, I'm pointing, but you don't see that. So in the left column, you see person, observation, condition, drug exposure, procedure. So this is really describing what basically has happened to a patient. But you can imagine that if you want to organize your medication prescription process, that's a different task, and that's not something that Omop intends to cater for. So if you want to establish that clinical process, then you might have to resolve or resort to HL7 FHIR. But once you have gone through all this process and you have collected all your data, then you can represent it using Omop Cdm, knowing what patient has been exposed to what drug to, for example, perform some study on drugs and efficacy and maybe side effects. So it deals largely, but not completely, with the same type of data, but with a different perspective. And the third I'd like to introduce is CDISC ODM, which is the Clinical Data Interchange Standards Consortium Operational Data Model. And this comes from the perspective that you capture patient information in a clinical trials setting. So its aim is to store and interchange study data, study metadata, so again, the models or the schemas, associated with clinical trials. And to establish this, CDISC provides an XML schema. And I've here added a small example where we see that we exchange information about some study ID on the first line. Then on the fourth line form data, we see it is demography. And on line 6, we see the subject ID. And on line 7, we see that the sex is female. So that's the description of the study subject. And then there's, in this case, measurements captured. That's the second bunch in the form data, which is the lab data, that there was a measurement of ALT with a result of 245. So this is really, and this is a format which is, for example, and especially in the US, mandated to be used by the Food and Drug Authority, FDA, to adhere to whenever you would want to get your medication registered with the FDA. So yet another perspective, one on clinical data, FHIR, one on analysis of observational data, Omop Cdm, and one focusing on clinical trial data, CDISC ODM. And in practice, we see all of this. So that's the reason why we thought, let's try to bring those together. And see if we can transform from one into the other, and explore that first with the set of common data elements for rare disease registration that was specified by the EU Joint Research Center. That provides a very small set of elements, which we are now working into a formal model, basically an RDF schema, which we see as part of the interlingua for the virtual platform, so that if we can transform the data that comes from ERNs, comes from registries, or their schemas, if we can make the conversion between that and this common language, then we can take further steps in establishing that virtual platform and the query builder. And the idea is that it will enable conversion from and to, or transformation, if you will, from and to HL7 Fire, Omop Cdm, and CDisk ODM. This is largely work in progress. We're taking steps. We're continuing to work on this. You may have seen some. You will see it in the future. Right now, I just list a set of modules that we've been working on. So there's pseudonym, which I think UBIT was shown on one of the slides, personal information, things about patient status, the care pathway, so that the care being provided to a patient, disease history, genetic diagnosis, and ultimately also things which are part of this common data elements set, things around consent, biobanks, and disability. So we intend to see where we can find those elements in Fire Omop CDisk to establish the transformation between those. So as a wrap up for this part, before I hand over to Mark for the final demo, well, it's important to realize there is no one-size-fits-all solution. There's no single format, no single model where we can say, okay, if everyone uses that, then all problems are solved. So we try to cater for the things that are out there and work with those. But it's important for ERNs to think what their data would look like when they make it available. So what format, what data model would you use, and would you adhere to, well, for example, more closely to Omop Cdm, or, and I think in general also, and that's especially with an outlook to the future, hopefully with these standards now establishing more and more, if people adopt and adhere to those standards from the point where they start to collect their data, it becomes much easier to make this data well, linkable, shareable, or at least queryable through this virtual platform. So it's important to consider whether and how you can adhere to, well, basically any of these standards. And adherence to a standard is, well, always better than trying to reinvent a wheel and yeah, just come up with your own specifications, because then you have to do the harmonization afterwards, and that may be challenging. So with that, I again hand over to Mark. Do you take control for your final demo?
I would love to take control. Okay. So my grandmother taught me to never do live demos using Teams. So it's not going to be a live demo, but I did screenshots of a live demo. So I guess this is the last talk of the day before we move into questions. The question is, how do we go from what you already have into these models that you just saw, the CDE models? So I want to talk about how we're going to do these transformations. So I'll give you an overview of what I'm about to show you, and then, so one of my favorite speakers says, you tell them what you're going to tell them, and then tell them what you told them. So I'm going to tell you the overview, and then we'll go through the demo and we can review at the end. So what we're going to do is use CSV as a lingua franca for registries. Now, Ronald has already showed you that CSV is one of the most limited of the data formats, but it's also the easiest data format to generate. You can get it out of spreadsheets, you can get it out of databases, you can type it in by hand. So we're seeing how far we can get just by using CSV. So what we're going to do is we're going to give you template CSVs, and you fill those templates with your data. We will then automatically pass that through a transformation pipeline using a set of technologies called RML and Yarmoul. And then we'll update your local FAIR data store with this transformed data. So that's the demo I'm going to give you now, but let's talk a little bit about the technologies themselves. So RML is a mapping language. So you can start with many different formats, databases, CSV, which is the one I'll show you, TSV, XML, JSON, and it will then map those into a linked data format. And you'll see that these are fairly contemporary technologies. So July 2020, and it's still an unofficial draft. So when you think about it, the things I'm going to show you that we're doing could not have been done at the beginning of the EJP project. These are fairly emergent technologies. So I want to recognize Anastasia Dumont for this technology. The next one, I'll show you on the next slide what it does. So on the left, we have a CSV with its input. It's difficult to explain this without having a pointer. In the center, you have an RML mapping. And on the right, you have the output RDF. So if you look at just the line that says template airportexample.com and then the ID in red in the middle, that little red ID is pointing to the input ID column. And if you look now at the bottom of the RML mapping, you have this latitude, which is pointing to the latitude column of the input. And what comes out of on the right is the subject predicate objects that are defined by these mappings. Now, it turns out that RML is quite difficult to use. So I'll show you in a moment a slightly easier technology than that. But let me show you from your perspective what you're going to see. So I have created documentation just I guess in the last week for all of the CSV templates. So what you're going to see is, for example, the personal information CDE, and then I tell you what the columns are. So they are PID, unique ID, sex URI, sex label, and birth date. So we give you that template, you create the CSV that matches it, and I tell you here what every one of those columns means, and in the case of sex URI, what the allowed values could be. So in this case, we're using the NCIT ontology, the National Cancer Institute thesaurus, to define female, male, undetermined sex, or unknown sex, which you can use in the case of undetermined fetal. And then we say, for example, birth date has to be compliant with ISO 8601 standards. So we give you that, you then fill those columns with your data, and that's the last thing you do. After that, so here's some sample data. So anonymous patient IDs, some unique identifier, there's the URL for the NCIT, they are male, and there's the ISO formatted date. We then have published a set of Yarmoul templates. Yarmoul is a standard that writes RML, because RML, as I told you, is quite difficult to write and quite difficult to maintain. Yarmoul is a lot easier. It's easier to read, it's easier to maintain, and we plan to provide training in Yarmoul so that you can, in fact, edit these files yourself if you feel that you need to or you feel you want to. And again, these are fairly contemporary technologies, April 2020. So we're really bleeding edge. So this is what Yarmoul looks like. I don't want to make a big fuss about it, but you'll just see that it's quite similar. So we have clauses. So on the left we have, for example, person has a role of a patient. And on the right, where the red circles are, there's an age measuring procedure. Age measuring procedure has an output, and that output is a birth date. And again, the birth date is pointing to the birth date column in the CSV, which has that value. And so when those triples are created, they will the values will be taken from every row in that CSV. So here's the library of templates. So we have the care pathway, we have the diagnosis, we have the disease history, disease progression, genetic diagnosis, patient consent, patient status, and so on. Every one of those has the Yarmoul template and its documentation, just as I showed you, so that you can understand what the template is about and how to use it. But in principle, you don't need to, because we'll do this for you automatically. What I'm going to show you now is a fully manual approach to doing the transformation. You will never have to do this, although you may want to if you decide to edit the Yarmoul yourself, because this will be a way that you can test what you've done and make sure it works. So I'm going to show you a website called Matey, which is again from Ghent University. This is what the Matey interface looks like. On the left-hand side, you have an input box for the CSV. In the middle panel, you have an input box for the Yarmoul. It's nicely color-coded, so you can more easily see it. You can more easily debug it, edit it, and so on. And then at the top, there are two buttons. One is to generate the RML. So remember that Yarmoul is a language that generates RML. So the first thing you do is click that button. And when you click that button, the bottom panel gets full of RML. And I think this is a good example of how much more complicated RML is versus Yarmoul. So Yarmoul is a really nice, easy to read format that, again, we hope that you will be able to edit by yourself at some point. We'll do some training on that. After you've generated the RML, you look at the green button, which is Generate Linked Data. You click that button, and there's your linked data, happy linked data. So this is a good debugging system if you want to do things manually, but that was only for the purposes of this demo. So our CDE in a box, as we call it, is going to automate all of that. So what will happen is you will start up the CDE in a box. The CDE in a box will automatically download the database of Yarmoul transforms. You will drop your CSV files into a particular folder, and it will automatically be transformed and automatically pushed into what we call the fair data point, or a triple database, together with metadata and other things. So in principle, your only task will be to generate the CSV. Everything else will be automated for you in our CDE in a box.